Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a great pleasure to introduce Yuri Makarychev from Toyota Technological Institute at Chicago. He's visiting Microsoft Research for 3 days, and today he will tell us about satisfiability of ordering CSPs above average.
Thank you for the introduction. So I will talk about satisfiability of ordering CSPs above average, and I will show you that this problem is fixed parameter tractable. This is joint work with Kostya and with Yuan Zhou from MIT. So let me first define the problem, define what ordering CSPs are. So in an ordering CSP, we are given a set of n variables, x1, etc., xn, and m constraints pi 1, etc., pi m. And we want to find a linear ordering of the variables that maximizes the number of satisfied constraints. What are the constraints? So each constraint pi r depends on at most k variables, where k is a given constant, and each constraint prescribes what relative ordering of the variables it depends on are valid and which are not. Or in other words, for each constraint, we have a list of possible relative orderings of the variables it depends on. And if the ordering of the variables is in this list, then the constraint is satisfied. Otherwise, it's not. And let me just show you two very well-known examples of ordering CSPs. The first example is the maximum acyclic subgraph problem. In this problem, we are given a directed graph G on a set of vertices x1, etc., xn. And our goal is to find a linear ordering of the vertices that maximizes the number of forward-going edges. And it's easy to see that this problem is just an ordering CSP of arity 2. So each edge xi, xj corresponds to a constraint xi is less than xj. And then the number of forward-going edges is equal exactly to the number of satisfied constraints for every ordering of xi's, right? Another well-known example is the Betweenness problem. And in this problem, so this problem is basically an ordering CSP of arity 3. And in this problem, all constraints of the form xi lies between xj and xk, or more explicitly, of the form xj is less than xi less than xk, or xk is less than xi less than xj. What is known about ordering CSPs? There is a very simple trivial approximation algorithm for the problem. Let's just randomly permute all xi's and output a random ordering. How well does this algorithm perform? For the maximum acyclic subgraph problem, this algorithm satisfies each constraint with probability half, right? Because for every xi and xj, two possibilities are equally likely, that xi is less than xj and that xj is less than xi. And therefore, this algorithm satisfies m over 2 constraints in expectation. And let's denote this number, the expected number of constraints this algorithm satisfies, by AVG, average. For the Betweenness problem, this algorithm satisfies each constraint with probability 1/3, because each of the 3 vertices the constraint depends on are equally likely to be between the other 2. And so in expectation, this algorithm satisfies m over 3 constraints. Now, this algorithm is very basic, almost trivial algorithm. And it's natural to ask if we can do better than this algorithm. And in general, this problem for different types of constraint satisfaction problems has been studied a lot. So the basic question is to get some advantage over a trivial random algorithm get advantage over random. And the first result in this area was due to Hosted, who showed that and he studied regular CSPs, not ordinary CSPs, that the 3CNF and 3XOR CSPs are approximation resistant, meaning that no approximation algorithm gets a better approximation ratio than this trivial random assignment algorithm. And if there is no non-trivial approximation for a constraint satisfaction problem, we call this constraint satisfaction problem and the corresponding predicate approximation resistant. And it's an interesting question to classify all like regular predicates, which of them are approximation resistant, which of them are not. We still don't have the complete classification. For instance, Austrian and Mossel proved that a very wide class of predicates that kind of come from pairwise independence are approximation resistant. There are also some positive results showing that some CSPs are not approximation resistant. For instance, Hosted showed that any 2 CSP is not approximation resistant, and also Hosted showed that bounded occurrence CSPs are not approximation resistant. But there are many, many results in this area, and there are still many open problems. This problem, the advantage over random, was also studied for ordinary CSPs. And let me first tell you about positive results, and then I will tell you about negative results. So first, Berger and Shor, very long time ago in 1990, showed that we can get advantage over random for bounded occurrence instances of the maximum as acyclic subgraph.
So does this bounded degree?
Yes. And then in a joint work with Charikar and Kosta, we showed how to get some advantage over random for the maximum acyclic subgraph in general graphs, and the dependence is different. Goswami and Zhou showed that we can get advantage over random for any ordinary CSPs of arity 3 that have bounded occurrences of variables, and this result was generalized to all bounded occurrence CSPs by Kosta. On the negative side, Goswami, Hosted, Manakaran, Raghavendra, and Charikar showed there is no non-trivial multiplicative approximation algorithm for any ordinary CSP of any arity k. So unlike assignment CSPs, there is no better approximation algorithm for any ordinary CSPs. Or formally, this means that no polynomial time algorithm can find a solution satisfying at least 1 plus epsilon times average constraints for instances with optimum greater, even for instances with optimum greater than 1 minus epsilon m for every constant value of epsilon. So in other words, no algorithm gets a, so we can't get any constant factor advantage over random, right? And then it's natural to ask if we can get at least some additive advantage over random. So we cannot improve the approximation factor. Maybe we can just do a little bit better than random. And this question was posed by Gutin, Van Iersel, Mnich, and Zhou, who conjectured that there is a fixed parameter algorithm that decides whether the optimum is greater than average plus t or not. And here t is a fixed parameter. So in other words, this means that there is an algorithm whose running time is some function of t, and this function may be, for instance, exponential in t times a polynomial in m plus n that answers this question. So that decides whether the optimum is greater than average plus t or not. What is known about this conjecture? First of all, let me mention that a similar conjecture was proved for assignment CSP. So Alon, Gutin, Kim, Sider, and Yeo showed that for any assignment CSP, regular CSP, like the counterpart of this conjecture is true. For ordinary CSP, there has been a number of papers, and by Gutin et al., who showed that this conjecture is true for the maximum acyclic subgraph problem, for the Betweenness problem, and finally for all ordinary CSPs of arity 3. However, in general, the problem seems to be much more difficult, and in particular, Gutin et al. Noted that it appears technically very difficult to extend results obtained for arities 2 and 3 to arities greater than 3. And in this paper, we show that this conjecture is true for CSPs, for ordinary CSPs of all arities. And also we generalize this result and show that actually a similar conjecture is true for a very wide class of constraint satisfaction problems that have some structural properties. And in particular, this class includes all ordering CSPs. And I will say a few words about that later. Also, to prove our results, we prove a new Bonami-type lemma for the Efron-Stein decomposition, and we believe that this result is of independent interest. And I will say a few words about this result later, and I will also define what the Efron-Stein decomposition is. At the high level, we use the approach of Alon et al. That they used for proving the counterpart of this conjecture for regular CSPs. And recall that in this problem, we are given an instance of an ordering CSP and a parameter t, and we need to decide whether the optimum is greater than average plus t or not. And we prove that there are two possibilities. The first possibility is that the instance depends on at most quadratic in t number of variables. So in this case, we can just try all possible orderings of these t-squared variables, find the best solution, and test whether the value of the solution is greater than average plus t or not.
So k has to be fixed also?
K is fixed. So we assume that k is fixed and t changes, but the running time may depend on t. For different values of k, we can have even different algorithms.
But when you said that was a fixed parameter tractable for all arity, you meant for all?
For every k, there exists, it's true, but the polynomials may be different. In particular, here, this constant ck depends on k. Any questions? Yeah, let me know if you have any questions about the problem or the statements. And also, here, this set of variables is called a kernel. And so in this case, we have a kernel of quadratic in t size. And in the second case, the instance depends on more than ck t-squared variables. And in this case, we show that actually the optimal value is greater than average plus t. So in this case, we know that the answer is positive. Moreover, in this case, we can actually find a solution whose value is greater than average plus t, but of course not necessarily the optimal solution.
What's the canonical form I should think for large k?
So of an ordering CSP.
Yeah.
Yeah, so we can always assume that all constraints of the form xi1 is less than xi2, etc., is less than xik. So if we replace, because for every constraint, we have a subset. So each constraint is just a conjunction of such clauses, and then we can just replace it with these clauses. Then the number of constraints will go up, but the optimal value will not change, and the expected number of satisfied constraints will not change.
So each one is like average is basically 1 over k factorial for such things.
Yes, yes, for such constraints, yes. Any other questions? Okay, now how do we prove these that there are only these two possibilities? First, let's consider a random ordering of x1, etc., xn, and let's denote by z, capital Z, the number of constraints satisfied by a random ordering. And then by definition, the expectation of z is equal to this number avg, right? Now, first we prove that if the instance depends on at least r variables, then the variance of this random variable z is large. It's at least some positive number constant a times r. And so if we are not in case 1, if the instance depends on many variables, then we know that the variance is high. Now we prove theorem 2 that says that if we are not in the first case, so if the variance is high, then the optimum is greater than the average plus some positive constant times square root r. And here I want to know that this result is not trivial in the sense that, of course, if the variance is high, then the standard deviation is high. And we know that this random variable z deviates from the expected value by at least square root r, right? But the distribution of z is not necessarily symmetric, and moreover, in most cases, it's very asymmetric. So we don't know whether it deviates only in one direction or in both directions. So it's possible that it takes some values that are much smaller than the expectation, but it never takes values that are considerably greater than the expectation. And what this theorem shows that actually, in this case, for this random variable z, we still have a guarantee that z attains values that are considerably larger than average. And now, as a corollary, we get that if the variance of z is at least h squared, then the optimum is greater than average plus t. So we are in case 2, and we know that the answer is positive. So this is our plan.
Theorem 2, what are the conditions? Sorry.
So z is our random variable, the number of satisfied constraints.
For any ordering CSP, no?
For any ordering CSP.
It doesn't. You're not assuming the boundedness, and there's no. Yeah. Okay.
I mean, we assume that k is fixed. The number of variables each constraint depends on, but other than, and yeah, I mean, this constant b depends on k. So now we need to prove two theorems, with theorem 1 and theorem 2. And to do so, we use the Fourier analysis, and more specifically, the Efron-Stein decomposition. Also, in order to prove this theorem 2, we prove a Bonami-type lemma for the Efron-Stein decomposition, and I will tell you about that in a few moments. And so we want to use Fourier analysis to solve this problem. One problem is that Fourier analysis works especially well on product spaces. And in our case, the set of solutions is not a product space, right? So the set of solution is a set of permutations of variables x1, etc., xn, and it's not that convenient to use Fourier analysis on this set. So let's instead assume that each variable xi belongs to the segment 0, 1. And then if we assign values to x1, etc., xn from this segment 0, 1, then we can consider the corresponding linear ordering of xi's, right? Xi's are just ordered according to their values. Moreover, if we assign values to xi's randomly, then this ordering will be also random, and we will be distributed uniformly, right? So this is our plan. And here I want to mention that it's very important that this domain 0, 1 is a continuous infinite domain. So some previous approaches to this problem, I mean, and some of the papers I mentioned on ordering CSPs use a so-called bucketing technique. So what they did, they considered a fixed domain of bounded size and assumed that xi's belong to this domain. In this problem, we can't use this approach. So we cannot use a fixed domain of constant size instead of this segment, 0, 1, because if we try to do that, we will not preserve the optimal value. And so this approach will not work. In order to preserve the optimal value, we can take a very large domain of size n or polynomial in n. But that approach will not work because then all the parameters will depend on n, and in particular, the size of the kernel will also depend on n. And so we will not the result we want to get. So it's really crucial here that our domain is fixed. It doesn't depend on n, and we can use it. Now I want to define the Efron-Stein decomposition. And roughly speaking, the Efron-Stein decomposition is very similar to the Fourier analysis on the Boolean cube. So if you have a function on the Boolean cube, then we can write it as sum over all subsets S of the set of numbers from 1 to n, the Fourier coefficient corresponding to this set S times the character for S. And it has the following very nice properties. First of all these functions fs, chi-s, depend only on variables in this variables xi with I in S. Then all these functions are mutually orthogonal. And in particular, because of that, the variance of f is just equal to the sum of variances of its Fourier terms. And also, we have linearity. We have this property for the standard Fourier analysis of Boolean functions. Now, the Efron-Stein decomposition has very similar properties. So now let's assume that f is a function from the cube, the segment 0, 1 to the power of n to real numbers. And the Efron-Stein decomposition is a representation of f in the form like this. Actually, we can write the Efron-Stein decomposition for function defined on any probability space. So here, this set doesn't have even to be the set of the segment 0, 1. And it has very similar properties. So first of all, each function fs depends only on variables xi with I in S. Then all functions fs are mutually orthogonal. And because of that, the variance of f is equal to the sum of variances of these functions fs. And the decomposition is linear. Let me now define the Efron-Stein decomposition. And I will not be very precise, but let me just tell a few words that explain what the Efron-Stein decomposition is. And let's first start with the case n is equal to 2. And moreover, let's assume that f is a product of two functions. Is a product of two functions g and h. And let's write f as the expectation of f. So g empty set is the expectation of f. And g1 of x1 is just g of x1 minus the expectation of g. And similarly, let h empty set be the expectation of h, and h2 of x2 be h minus its expectation. Then clearly f is equal to this product. Now we expand this product, and we get this expression. And in this expression, the first term is this function f empty set. This function depends only on x1. So let's f1 be this function. This will be f2, and this will be f12. And now let's assume that n is greater than 2, and again, f is the product of terms like this. Then we just decompose gi in a similar way. So we write that gi is equal to its expectation plus gi minus its expectation. We substitute each gi in this product by the corresponding expression, and then expand that, and we get 2 to the power of n terms. And each term is a term in the Efron-Stein decomposition of f. And in general, of course, f is not necessarily a product of n functions, but we can extend this definition by linearity, and we will get a valid definition for all functions f. So this is the idea behind the Efron-Stein decomposition. Do you have any questions? Should I say more about this?
Like those functions generate space of buffer?
So in particular, what we can do, we can consider the standard Fourier decomposition of f, right? And let's say these functions may be sine and cosine functions. And then we can represent f as the sum of, say, sine of x1 times cosine of x2, sine of x3 with some coefficients. So it may be sine of 5x5 and so on. And then we apply this to each term.
So is there a way to have a more one-shot description of this decomposition using just directly the Fourier decomposition, the usual way?
Yes. So what we can do, so we have the Fourier decomposition. So suppose that we have a Fourier basis phi 0, phi 1, phi 2, etc., infinite Fourier basis. And let's assume that phi 0 is the constant function, so it's equal to 1, right? Then what we can write that f is equal to sum of f, phi, let's say I1 of, phi I1 of x1, phi, let's say I11, I12 of x2, and so on, phi n of xn. And now what we can do, we can define fs is the sum of these terms where this index I, so some of those terms k such that I k j is equal to 0 if j is an S. So in other words, okay, let me say that in other terms, so what we do, we have this infinite number of terms here, right? And now we kind of, and we have, now we want to find these 2 to the power of n terms. So for every set, we have a term. And now we want to assign each term to one of these sets, right? And the term for each set will be just the sum of the functions which we assign to the set. And so we look at one product like this, and look at those terms, at those functions phi that are not equal to 1. So basically, I mean, if for instance this function is equal to 1, this is x2, this is, say, I don't know, sine of x3, right? And this is again 1, then this term, in this term depends only on x2 and x3 non-trivially. So we put it in this cell corresponding to the set 2 and 3. And this is how we get this decomposition. This is another explanation. Also, we can actually write very simple explicit formulas for computing the Efron-Stein decomposition. And the Efron-Stein decomposition is defined uniquely. So there is only one Efron-Stein decomposition for every probability space. So first, we define these functions f subset t by this formula. So it's the expectation of f given xi's with I in t. And then we use the inclusion-exclusion formula to get this expression for fs. OK, now let's apply the Efron-Stein decomposition to our problem. So recall that we consider this random variable z, which is a number of satisfied constraints. And we can just use these explicit formulas to compute the Efron-Stein decomposition of z. And what we get, first let's know that z is just the sum of indicator functions of basic ordering predicates of this form x1 is less than x2, etc., less than xk. And because the Efron-Stein decomposition is linear, it's enough to compute the Efron-Stein decomposition of just these predicates. And here we just use those formulas, and we get that the decomposition has this form. So it's some constant times sum over all permutations of the indexes 1, etc., k. And here, some polynomial p with integer coefficients that of degree at most k that depends on variables x1, etc., xk, and times the indicator of the event that i's are ordered according to pi. So we get that the decomposition has this form, and because the Efron-Stein decomposition is linear, we get that the decomposition of z also has this form. Now, what is important here that these polynomials phi prime have integer coefficients. And so the set of all functions of this form forms a discrete lattice in a finite dimensional space. And because of that, if this term zs in the Efron-Stein decomposition is not identically equal to 0, then it must be bounded away from 0. And specifically, its variance should be at least some number that depends only on k, some positive number. And to prove that, we use a very basic compactness argument. OK, now we are ready to prove our theorem 1. So recall that we assume that the instance depends on at least r variables, and we want to prove that the variance of z is large. So we compute the Efron-Stein decomposition of z, and now know that each term zs depends on at most k variables, right? Because each predicate depends on at most k variables. Therefore, and since z depends on at least r variables, therefore there are at least r over k terms, right? Each term contributes at least bk to the variance of z. And so what we get that the variance of z is at least rbk over k. So it depends linearly. It's lower bounded by linear function of r. And so this concludes the proof of theorem 1. Now we want to prove theorem 2. And the plan is as follows. So what we want to prove is that if the variance of z is large, then the optimal value is at least average plus b square root r. And we show using a new Bonami-type lemma that we prove and which I will show in the next slide. Then the fourth moment of z is upper bounded by some constant that depends only on k times the variance of z squared. And from this, it follows by result of Alon et al. That z attains values greater than the average plus b square root r with positive probability. And this result of Alon et al. is similar to the Markov inequality, so it's not difficult to show. So let me now say a few words about this Bonami lemma. And so what we show that, let's first recall what the standard Bonami lemma for -1 random variables is. So the Bonami lemma says that if f is a polynomial of degree at most k, then the fourth moment of f is bounded by some number 9 to the power of k times the second moment of f squared. Now what we prove that if f, so let's consider a function f now from the segment 0, 1 to r, or this also works for any probability space. And let's assume that all terms in the Efron-Stein decomposition has degree at most k. Then a very similar inequality holds. But we also need to assume additionally that this condition is true, that the expectation of the product of any 4 terms is bounded by the product of the variances times some number. And a condition like this is necessary. So without this condition, this lemma is not true. And we use this for ours. In our problem, we show that this condition is true, and we get that the fourth moment is bounded by the second moment squared. So this is how we apply this lemma in our case.
So if I take a function like a polynomial on like of degree k, so if I extend it now on the continuous hypercube now,
Right.
Does it does it have Efron-Stein decomposition of degree k?
If we extend it,
Yeah. So extend by just saying just round it, right?
Right.
Yeah.
But by doing what? By rounding it or by linearity, kind of by
linearity. Just
so we consider the same polynomial.
Yeah.
It will have an Efron-Stein decomposition, but it will be different from.
It won't be.
It
won't have degree k.
No, yeah, it should have degree k. Yeah. It will have degree k.
And what would the last condition mean in that case? Is that trivial?
If we just take this function, it should be true.
Okay.
So for kind of normal function, it's true. So basically, it's a problem if the function is unbounded. If it's bounded by some constant, yeah, it will be true. And yeah, I mean, it will hold this small constant c. Any questions? So let me now tell you how we prove this Bonami lemma for the Efron-Stein decomposition. And the idea is to reduce this problem to the standard Bonami lemma. So we are going to define an auxiliary polynomial g, and we proceed as follows. So let gs be just the variance of this term fs, and let chi s be the character for the set s. And so we define this polynomial g with Fourier coefficients gs. And now we want to compare f and g. And the distributions may be very different, but we want just to compare the second and fourth moments. And note that since f has a Efron decomposition of degree at most k, g is a polynomial of degree at most k. First of all, by our choice of Fourier coefficients, the variance of g is equal to the sum of gs squared, and this is equal to the sum of variances of terms fs. So this is equal to the variance of f. So these two functions have the same variance. And now what we want to prove, so we want to upper bound the fourth moment of f. Now we want to, what we are going to prove that the fourth moment of f is bounded by the fourth moment of g times some constant c, and using the standard Bonami lemma, this is less than some number times the variance of this is the variance of g squared, then the variance of g squared, and this is equal to the, again, to the same constant times the variance of f squared. So this should be just f. Okay, so this is our plan, and the only thing that we have to prove is this inequality, right? Then the fourth moment of f is upper bounded by the fourth moment of g. And let's just expand the fourth moment of f. So the fourth moment of f is equal to the sum over subsets S1, S2, S3, S4, the expectation of the product of fs1, fs2, fs3, fs4, right? And the fourth moment of g is given by this formula. Okay? Now, we want to show that this inequality holds term by term, so that we can just write that this term for every set S1, etc., S4 is less than the corresponding term here. And recall that this additional condition that we require says that the product, the expectation of the product of fs1, fs2, fs3, fs4 is less than some constant c times the product of the variances of g si squared. So basically, we get that this coefficient is greater than this expectation up to this constant c. So now the only thing that we need to show is that this expectation is at least 1. Now, and here we have a slight problem. So if some variable doesn't appear in these sets S1, S2, S3, S4, then okay, what we have here just the product of variables z, right? And we can write as variable z1 to some power times variable z2 to some power and so on, and these variables are independent. So we can consider each variable separately. Now, if some variable doesn't appear in this sets S1, S2, S3, S4 at all, then of course it doesn't contribute anything. If a variable appears one time, then its expectation is 0. And then this expression is also 0. But it's not hard to see that in this case, if some index appears in this sets only once, then this expectation is also 0. So that's not a problem. If a variable appears 2 or 4 times, then the expectation of its square and its fourth power is equal to 1. So we are in good shape. There is a problem, however, if a variable appears 3 times here and 3 times here. Because in this case, this expectation is equal to 0, and this expectation is not necessarily equal to 0. However, it turns out that this is easy to fix. So basically, instead of considering plus minus 1 variables, we consider a Bernoulli variable with 0 first moment, but with positive first, second, and with positive second, third, and fourth moments. And specifically, we just consider a random variable that takes values 3 and minus 1 with probabilities 1 quarter and 3 quarters. This variable has expectation 0, but it has positive first, second, and third moments. And so instead of, and we correspondingly consider characters for this variable. We also need to show kind of the analog of the standard Bonami lemma for functions defined on this probability space, but it turns out that this is very easy. And then from that, we get the result of this. We get this Bonami lemma for the Efron-Stein decomposition. Any questions?
Where that doesn't hold, and also that condition on the board.
This one. I mean, basically, if the function belongs to L2 but doesn't belong to, I mean, if this function, right? So even if all these terms are equal, if the function belongs to L2 but doesn't belong to L4, then this is infinite and this is bounded. Any questions? OK, and using this Bonami lemma for the Efron-Stein decomposition, we get Theorem 2. So this concludes the proof. Now let me mention our other result. So we prove actually our result for a wide class of constraint satisfaction problems defined on domain 0, 1. And it holds for all CSPs that have certain structural properties. In particular, it holds for CSPs with constraints defined by linear equations with small integer coefficients, or with constraints defined by inequalities, or which are defined by bounded degree polynomials with small integer coefficients. And just to give you some idea what these constraints might be, for instance, we can have constraints of the form xi is greater than the average of xj and xk, or say xi is closer to xj than to xk. Also, all ordering CSPs are in this class. They can be defined by trivial linear inequalities, and also all standard assignment CSPs are in this class. OK, let me summarize what we do. What we did, we proved the conjecture of Gutin et al. And moreover, we generalized it to a wide class of constraint satisfaction problems. And additionally, we proved a Bonami-type lemma for the Efron-Stein decomposition. And it would be interesting to see if it has more applications in computer science. Thank you.
Questions?
Are those CSPs also approximate? Is it clear that for the last ones that you mentioned, that you possibly cannot get multiplicative?
I mean, so this class is very generalized as I describe it, and in particular it includes all ordering CSPs. So yes, we can't approximate them, but I mean if you consider some subclasses, then they're not that difficult. I mean in particular, or just standard CSPs belong to this class of CSPs, and for many of them we do have good approximation algorithms. Yes.
So it's funny because the algorithm at the end is very simple. And could you expect maybe to take more out of your analysis and get a better algorithm with complexity maybe 2 to the t instead of 2 to the t squared?
I don't know. But I think
you would be in case 1 and you would say, I don't know, something like, something more refined than just R variables and that.
I don't know.
There is no obstruction.
Yeah, I'm not sure. I don't know. I think that it might be possible. And I mean, of course, it might be possible to have some improved approximation factor, but by improved not by a constant, but by something else. For instance, maybe it's possible to get the result of the form that we can get 1 plus 1 over log n times average, or maybe something along that line.
So is something like this known for max acyclic subgraph?
For what?
The max acyclic subgraph?
For the maximum acyclic subgraph, we can get average plus opt minus average divided by log n. So that's basically, this is,
Average is just half the edges, right?
yes. So this is an approximate, I mean, so for the maximum acyclic subgraph, we can look at kind of at a different objective, what is our advantage over random, right? And then for this function, this is a log n approximation factor. This is a log n approximation algorithm.
And in general? Yeah, so but that's not exactly the approximation you wrote earlier. So does it generalize to all permutation CSPs?
This result?
Yeah.
No. I mean, that would be really interesting to get something like that for other ordering CSPs, but that's not.
These techniques are very different from these ones? Or?
For this result, the technique is a bucketing technique. Yeah, I mean, the technique is very different. So we use here bucketing. So we use here bucketing. Here we can't use bucketing as is, and after that it's very different. I mean, it's funny that here we also use Fourier analysis, but the Fourier analysis is very different from this Fourier analysis. Any questions?
More questions? Let's thank this for being here.